Humans are perfectly adapted to exactly one environment. Earth provides us with breathable air, liquid water, comfortable pressure, and a dense, protective magnetic field. Stepping off this planet requires a total shift in how we stay alive. Every breath, every calorie, and every degree of temperature must be manufactured and managed by a machine. The Moon is our closest realistic frontier, but it offers nothing to support biology. It has no atmosphere, a fraction of Earth's gravity, and no natural shield against the constant bombardment of cosmic radiation. To survive here, we would depend entirely on pressure suits and heavily shielded architecture. A future base might sit near the lunar poles to mine ice for water and fuel, while burying its living quarters under meters of lunar soil to block radiation. This first step into space forces us to retreat from the outdoors, moving into engineered, sealed environments, where technology replaces the natural world. Mars is the world that looks most like a second home. It features familiar seasonal changes, polar ice caps, and a day-night cycle nearly identical to our own. But those familiar patterns hide a freezing, irradiated desert. The Martian atmosphere is paper-thin and composed almost entirely of carbon dioxide, providing no oxygen and no insulation from the cold of space. Sustaining a colony here requires a massive industrial footprint. Settlers would live in pressurized surface domes or deep underground modules, relying on mechanical systems to claw water and oxygen out of the dry soil. Survival on Mars means spending a lifetime inside a fortified mechanical bubble, isolated from the planet's surface by layers of steel and life support hardware. Venus presents a different kind of barrier. Its surface is a toxic wasteland, where the atmospheric pressure is high enough to crush a submarine, and the heat is high enough to melt lead. However, 30 miles up into the Venusian sky, the environment changes. At this specific altitude, the temperature and atmospheric pressure drop to levels almost identical to sea level on Earth. Since breathable air naturally floats in Venus's heavy carbon dioxide atmosphere, settlements here would take the form of massive airships and floating platforms drifting safely above the clouds. In the outer solar system, Jupiter's moon Europa hides a global ocean beneath miles of ice. While the water is promising, the surface is constantly bathed in lethal levels of radiation from Jupiter. To reach that water, researchers would have to burrow deep into the crust, using the thick ice shell as a natural radiation shield for their living quarters. Saturn's moon Enceladus offers a similar subsurface ocean, but it actively sprays plumes of water vapor and organic material into space, allowing us to collect resources without drilling through the ice. These extreme worlds dictate our designs. To stay alive, we must drift above the acid of Venus, or hide miles beneath the ice of Europa. Saturn's largest moon, Titan, is the only moon with a thick atmosphere. While this air blocks radiation, it is hundreds of degrees below freezing, with lakes of liquid methane carving the landscape. Living here requires massive energy for heat. Settlers would need heavily insulated domes to prevent their living spaces from freezing solid in the cryogenic environment. Closer to home, the dwarf planet Ceres sits in the asteroid belt. It possesses a cold, rocky surface with virtually no gravity and no atmosphere. A settlement here would function as a sealed industrial mining base, focused entirely on extracting water ice from the rock to refuel ships moving through the solar system. The outer solar system provides strategic resources, but every location demands a unique and complex engineering solution just to keep humans breathing. Pacing quickens. Our search for homes reaches beyond our solar system to worlds like Proxima Centauri b. Because this planet orbits so close to its star, it is likely tidally locked. One side is baked in constant light, while the other is trapped in a permanent frozen night. Any habitat here would have to hug the narrow twilight zone, the border where temperatures between the two extremes might be manageable. TRAPPIST-1e is an Earth-sized candidate, but its extreme distance means any settlement would have to be 100% self-sustaining. There is no possibility of help from Earth. We also look to Kepler 452b, which is often described as an Earth-like cousin. But look at the data we actually have. The readings for gravity, atmosphere, and water are empty. Their actual status is purely theoretical. A world can have Earth's mass and still possess crushing gravity or a toxic atmosphere that would kill a human instantly. A world that looks Earth-sized through a telescope does not guarantee a world where human biology can survive. Because natural planets come with fixed hazards, like low gravity and radiation, engineers have proposed a different path, building our own worlds from scratch. Instead of fighting planetary environments, we could construct massive, rotating space habitats. By spinning these structures, we use centrifugal force to create artificial gravity. Massive mirrors would capture and direct sunlight into closed ecosystems on the interior. Planetary colonies are limited by the rocks they sit on. These habitats offer something no planet can, a world designed specifically for human biology, from the strength of the gravity to the contents of the air. The roadmap is becoming clear. The Moon is a reachable step. Mars is a difficult industrial outpost. Icy moons are remote research stations. Artificial habitats are the custom-built future. Humanity's future beyond Earth depends on our ability to package and transport our own life support systems. Wherever we go, we will be bringing a piece of Earth with us.